It's 7:37 in the morning on June 8, 2026. In General Santos City, children are lining up for the flag ceremony. 700,000 people are starting out another sweltering Monday on the southern coast of the Philippines. Then the ground violently ruptures. 33 kilometers below the ocean floor, a massive section of tectonic plates snaps. The magnitude 7.8 earthquake throws cars off the road and turns the morning commute into a desperate scramble for survival. Within minutes, schools and commercial blocks are reduced to fractured concrete and twisted rebar. 35 people lose their lives, and hundreds more are injured as rescue teams begin tearing through the rubble in the blistering heat. Seismologists can explain exactly how mechanical stress built up along this fault line over decades. Plate tectonics is well understood. What remains stubbornly difficult to answer is why it snapped on this exact day, at this exact minute. To explore that timing, we have to look 150 million kilometers away, to what was happening on the surface of the sun in the exact moment the fault gave way. This satellite imagery shows a massive coronal mass ejection erupting from the sun. In the days before the earthquake, active regions on the solar surface launched back-to-back plasma clouds, creating what heliophysicists call a cannibal CME, one storm catching and consuming another on its way toward Earth. By the morning of June 8th, that consolidated wall of solar energy was slamming into our planet. The National Oceanic and Atmospheric Administration had issued a G3 warning, a severe and rare geomagnetic storm alert, for the exact time frame of the earthquake. Forecasters were tracking the high-energy electron flux as it crossed the 1,000 critical threshold. They watched in real time as solar radiation began degrading high-frequency radio communications and straining satellite operations. We have a catastrophic rupture of the Earth's crust occurring simultaneously with one of the most intense space weather events of the year. The scientific community is currently divided on whether this is a mathematical coincidence or evidence of a physical connection between the sky and the ground. The idea that celestial events dictate earthly ones triggers immediate skepticism today, but mapping the relationship between the sky and the ground is the oldest scientific exercise in human history, predating modern geology by millennia. Early agricultural societies correctly linked the heliacal rising of certain stars to seasonal flooding. They mapped the phases of the moon to the rising and falling of the tides, generation after generation, relying strictly on observation. They lacked mathematics for orbital mechanics or gravitational theory, but their datasets were largely accurate. They recognized invisible forces governing their environment millennia before we had tools to measure them. The modern geophysicists and independent researchers comparing solar flare logs to seismographic data are participating in this exact same tradition. They are looking at recurring patterns in nature, asking if we're missing a physical mechanism. The observational data points to a recurring alignment. Active periods of solar weather frequently overlap with pronounced seismic and volcanic events, particularly along highly stressed boundaries like the Pacific Ring of Fire. Researchers refer to the potential mechanism behind this as magnetosphere-lithosphere coupling. It starts when a dense wave of solar plasma strikes the Earth, heavily compressing our planetary magnetic shield. That compression pushes energy downward, intensely agitating the ionosphere, the electrically charged upper layer of our atmosphere. Far below, massive tectonic plates are already locked in friction. The rock is saturated with mechanical stress, essentially waiting to fail. The hypothesis suggests that the severe disturbance in the atmosphere generates an induced electrical current that percolates down into the Earth's crust, interacting with the fault line. The solar storm does not generate the tectonic force required to move a continent. Instead, think of a massive concrete dam holding back a reservoir. It takes immense water pressure to cause a failure, but once the dam reaches its absolute limit, a tiny vibration can be the final trigger. If this coupling process proves accurate, the collapse in General Santos City was the terminal point of an energetic circuit that began 150 million kilometers away. Mainstream science remains appropriately cautious. Earthquakes strike every day, often during completely quiet solar conditions. Finding a correlation in a geologically noisy region requires navigating intense confirmation bias. Science relies on isolating variables. Until researchers can consistently separate a solar-induced trigger from the baseline rumble of the Earth, geophysicists will rightly demand extraordinary, measurable evidence. But the implications of this data demand rigorous investigation. If we can isolate a reliable, probabilistic signal between incoming solar storms and specific terrestrial stress points, we could integrate space weather data directly into regional hazard models. Identifying a solar seismic link would grant highly vulnerable communities a 24 to 48-hour window of elevated awareness. For the families standing in the rubble in Mindanao, the distinction between an isolated tectonic accident and a triggered event matters deeply. We have the satellite networks and the historical data needed to test this connection. We owe it to them to find out if, when the sun moves, the Earth answers.